Great to talk to everybody. I hope you all hear me and see the slides clearly. So I'm going to give you a summary today of SAMI and that new Hector instrument that we're currently building, and try to highlight some of the most recent science that SAMI's done. Of course, there'll be some other speakers coming straight after me that'll actually go into some more detail in particular bits of science, and I won't repeat those. But just for those of you who have don't completely know what SAMI is, which there probably are many by now. This is a survey that we've carried out at the AAT. We've observed over 3,000 galaxies with integral field spectroscopy over a number of years. We finished observations in 2018. We've released a lot of the data now as well, and our final data release, DR3, will be happening later this year. And really the aims around SAMI are about trying to put galaxies in context, understanding by spatially resolving them what the physical processes are that transform galaxies, how mass angular momentum build up, how gas gets into and out of those galaxies. And so it's really about galaxy evolution, but a really important part of the SAMI project is that we sit within this detailed measurements of large-scale structure. And so here on this slide, what you can see on the right-hand side are the gamma regions. So those wedges are, the black dots are gamma galaxies, and every individual colored dot, which will be hard to see because there are so many of them, is a SAMI galaxy, and the color coded by their spin or lambda r parameter. So red galaxies are what we might call slow rotators, and the sort of ones towards green and blue are your regular rotating disks. On the left-hand side, we see also the individual clusters we've targeted, again, the color-coded points. You're not meant to be able to see the great detail here, but just sort of get a sense of the way we're sampling large-scale structure. I can zoom in a little bit more. So the previous plot went out to redshift 0.1. If we just go into the region where we're sampling galaxies in a little more detail, up to redshift 0.06, and then you can see the large scale structure, individual SAMI galaxies in a bit more detail. And you can see we sample across a large range of structures. There's filaments and sheets, there's groups, and of course the clusters on the left-hand side. So a really important part of the project has been being able to both get spatially resolved spectroscopy, so you're actually observing the internal structure of these galaxies, their star formation histories, their dynamics, their gas state, but you're also putting them in the context of large-scale structure. You're able to understand the connection between their large-scale environment and their internal properties, and that was really one of the big drivers for this project. So just to give you a little bit of detail of where we're at so far, so the histogram there is the number of papers published so far by the team. Since the beginning of 2019, I think we've published 19 papers, and there's several papers that are currently with journals at the moment, and many more sort of in preparation. And a big focus of the team has been working on the papers that analyze the full sample that we finished observing a year or so ago. Again, the other focuses have been the DR3 preparations, which will happen in September this year, but also looking a bit further into the future, which is the Hector instrument. The Hector instrument build, and also planning for the survey that we will do with Hector. And I'll talk more about Hector towards the end of this talk. So obviously I'm not going to give you a highlight of every single SAMI paper we published in the last year, because that would blow my time out and yes, you'll start getting annoyed with me. But what I will do is highlight just a handful, just those top. So this is just in date order, the most recent ones at the top. So I'll just highlight 3 of the most recent papers we've just had published. 1 or 2 others that are on that list will be talked about in a little bit later in the session. So the first paper I'm going to talk about is actually by PhD student Julia Santucci. at UNSW. So Julie's actually a new ASTRO 3D member. And this was work done with her supervisor, Sarah Bruff, really looking at the spatially resolved information in terms of stellar populations within SAMI galaxies, and again, making that connection to their environment. Do we see differences in galaxies as we go across different environments? In Julia's case, what she was looking at was to try to understand whether galaxies that are the central galaxies, the dominant galaxy in their halo, have different stellar population distributions to satellite galaxies. So to do that, she was measuring gradients of those populations. So for example, measuring the gradients in metallicity or measuring the gradients in the stellar population ages. What you can see on these two graphs here, on the left-hand side is the gradient in metallicity, which is slightly negative, meaning that metallicity declines as you go to the outskirts of a galaxy, and it's plotted as a function of stellar mass. These points are the medians for the populations in those stellar mass bins, but the most important point here is that the magenta points and the blue points overlap each other, right? They don't, there's no offset, there's no difference between galaxies that are dominant galaxy in the halo and the galaxies of the satellites. This is also the case when you look at the age on the right-hand side. So we're really not seeing any evidence from the stellar populations, at least, that these galaxies are any different. What this suggests, because all these galaxies that Julie's looked at are passive galaxies, they're not currently forming star, what this suggests is that they're processes that quench galaxies, those environmental processes, don't seem to leave long-lasting traces in the stellar populations. The second paper I wanted to talk about was some work that Matthew Verdal, a PhD student at Sydney, has just recently had published. So this is Matthew's second paper from his thesis. His first paper was developing a new approach to getting precise measurements of the gas velocity dispersions within galaxies. Now, the gas velocity dispersion is a really important tracer of the turbulence and the gas processes that are going on inside a galaxy. And his paper from last year developed this program we call Blobby 3D that accounts for clumpiness in the gas distribution, as well as the beam smearing, the effect of the atmosphere smearing out the velocities. And so what we've done now is move on from that model. You can see examples of the fits to the model there from his 2019 paper, and actually start using that to look at how the velocity dispersion in galaxies is driven by different physical motivators and different is correlated to different parameters. So we use primarily the SAMI galaxies here, but also for the very highest star formation rate galaxies, we use some of the galaxies from the Dynamo sample, which is a Deanne Fisher and Carl Glazebrook and others have built up over some time. So where's my button to go forward? Okay, so I've lost my ability to click forward here. Oh no, okay, it's gone now. Okay, hopefully that's not going to lag and jump through all my slides in once. So here, I think, don't try to focus on everything. There's a lot of information here. Here, what we're just trying to do is to look at the correlation between velocity dispersion on the y-axis and a whole bunch of different physical parameters. So we've got mass, H1 mass for the galaxies that we have that for, star formation, and a whole bunch of other parameters. The key point here is that when we do this and look with a large sample across a range of different properties, the thing that correlates best is that case with the red box around it, which is star formation rate density. So the density of star formation seems to be the thing that is most correlated with the internal dispersion of the galaxy's gas. So that very much suggests that star formation is playing a role in driving the dispersion and driving the turbulence. We've gone a little bit further with this and actually compared it to some of the state-of-the-art models developed by Mark Krumholtz and collaborators. And so here's a comparison to those models in a couple of particular flavors of these models that Mark has generated. So in the top panels, we've got velocity dispersion versus star formation rate. And the low star formation rates, typically these velocity dispersions for the ionized gas measured from H alpha is about 15 kilometers a second or so. But as you get up to higher star formation rates, you start to see higher velocity dispersions. Now, the tracks on the top plots are model predictions, either what's called a transport and feedback model or a no transport fixed Q. Q is just a two-way Q stability parameter. And then what you can see on the lower panel is actually the residuals from those models, once you actually take into account, in particular, the fact that the model parameters also vary with the rotational velocity, which is what the color coding of the points are. In particular, here what you see is that a transport plus feedback model is in much better agreement than other models. Now that means that actually that gas transport in the disk is actually an important part of the process of star formation and contributes to the dispersion. One thing that's worth noting here is that it's really important for this sort of work that we get the dispersions right. We're working at or around or below a little bit the resolution of SAMI in the red arm. So you've got to use that higher resolution, but also modeling for beam smearing is really, really important. And there are other papers who have tried to do this with other data who have got much, much higher velocity dispersions, which are probably due to other systematics in the data rather than actually any physical process. So the last science highlight I'll talk about is simulation work that's been done by the UniSyd group. So this is by DJ Kim and Sukyong Yi. Pictures are there. That's DJ is the one in underwater. I couldn't get another photograph of him. This is about looking at how gas gets into galaxies, in particular doing that by looking at how the kinematics of gas, the motion of gas in a galaxy, differs from the motion of the stars. So what we're looking at is an offset in the position angle of the rotation axis between different galaxies, between their stars and their gas. An example of what you can see in a simulation here is on the left-hand side here, where a galaxy falling through a cluster actually changes its position angle dramatically as it falls through the cluster, and in particular, as it falls near to the center of the cluster. So the galaxy's path, I don't know if you see my cursor, but the galaxy's path is coming through here. Around this point, it's suddenly changing, the gas is being affected by the intercluster medium, it's changing its position angle, and then it comes through here. The actual position angle offset, in terms of degrees, is these blue points here, and it suddenly jumps up. And so what we're trying to understand is, comparing to SAMI data that we took and published a paper on last year, Julia Bryant led that paper, can the simulations actually show the same distribution of these misalignments? In terms of the statistical overall nature of the alignments, actually the simulations do a reasonably good job. What we're seeing here, the x-axis is the gas versus star position angle offset, the difference in the angle of rotation for the gas and the stars, and just the number on the y-axis. The orange is the SAMI galaxy measurements from Julia Bryant's paper last year, and the blue is the Horizon AGN simulations that DJ and Sukyong are using for this work. Now, what you see is that on the left-hand side, actually, it's in rather good agreement. So that means the simulations approximately are getting this right. However, there are a few things that are missing. One is that the SAMI data shows a small peak at 90 degrees offset and a small peak at 180, which is due to those being semi-stable configurations. And that really isn't seen in the simulations yet. We suspect that is simply due to the way the gas gets torqued in the simulations being a little bit different because of resolution effects within the simulations. However, it's also true that when you go to the clusters, which is the plot on the right-hand side, while the overall trends are right, we actually find that the simulations find many more misaligned galaxies in the clusters than the data does. Why exactly that's the case is not clear yet. Okay, so in my last few minutes, I'll talk about Hector. So SAMI used the existing A omega spectrograph on the AET and used a 1 degree field of view and was able to carry out a 3,000 galaxy survey. Hector, which has a new spectrograph currently being built with higher spectral resolution, which is key for many of the science goals for Hector. this instrument will have a larger number of, has larger resolution, it has a larger number of integral field units, so more galaxies, and will carry out a large survey starting next year to look in great detail at the internal dynamics and other properties of galaxies with this extra resolution, with this unique new spectrograph that we're building. So the schematic is down here, but the Hector project is progressing very fast. I just want to give you a few sort of notes on where things are at. Hector bundles these IFUs. There's an example of one on the right-hand side in that diagram. We just are doing final testing of the manufacturing process for these prior to sort of the final bundles being made starting in July. So that's going very well. All the optics and mechanical parts for the spectrograph have been delivered. And so the next stage for that is assembly. The oddly shaped black thing at the bottom left is the spectrograph mounting, sort of the frame to hold all the components. There's an awful lot of work going into the testing of the positioning system, particularly for newly manufactured components that we're currently getting. And there's also a lot of work happening on the integration of software as well, in terms of getting the system functioning from survey planning and preparation and targets all the way down to a configured field and observing. So that's currently, so there's a lot of activity and everything's looking really good right now. So where to next? My final slide. So as I mentioned earlier, SAMI Day Release 3 is planned for September this year. There's a large number of people in the team currently very active in producing final data products and also doing data quality control. Many people online here probably, in which case, thank you to all of those who have contributed so far. We're also working on approaches to for analysing data in different ways, and that's in collaboration with the various data scientists at Sydney University. But also there's still a large array of science that we are working on, and that includes kinematic classification, looking at different ways to connect the dynamics and kinematic measurements to large-scale structure, and a whole host of other things that you can see are listed there. And finally, what our expectation is that a Hector instrument build will see the instrument being shipped to the AET at the end of 2020 for a start to the survey in 2021. Okay, I'll finish there. Thanks.
Thank you, Scott. I'm glad to see the technology has made it all the way from Gallifrey across space and time. So it's time for Q&A. So I think there's 2 questions. Could you read those and maybe answer them live?
At the moment, I can't really see the question.
Okay, so the first question was from Claudia, and she asked, I just lost the window as well. So what I'll do, just stop remote control. So the first question was from Claudia, and she asked, what about the 0 point of the mass metallicity relation? Are there differences between centrals and satellites?
So we don't think so. Sam actually will show a little bit more on that a little bit later. He hasn't actually done the mass, hasn't looked yet at the difference between centrals and satellites. But he's particularly been looking at the mass metallicity relation and trying to reduce the scatter by measuring the gradients and calculating central metallicity. So maybe I'd say wait and see Sam's talk for that.
Okay, and then there is a second question as well from Mary Footman. Can you compare your velocity dispersions to those obtained with cold gas observations, H1 or maybe CO?
Yes, so look, that's a really, really interesting thing to do. And obviously the CO tends to be colder still. We've got a small number of galaxies that we've currently so far targeted with ALMA. There's various proposals to do more of that. There's a paper just about to come out. But those are, at the moment, they're mostly targeting particular objects. So they're, for example, targeting the wind galaxies that are interesting components. So we're looking for molecular outflows. But yes, it's a very interesting thing to do to target the galaxies with ALMA. We also have H1 for a bunch of these, but in most cases, not yet resolved H1 for most of these galaxies.
Okay, thank you, Scott. There's one more question from Matthew Collers, but I suggest we leave that for the normal Q&A. And I would also like to remind everyone that there is a Slack channel where all the talks will be posted afterwards, but it's also probably where we can have more extended discussions. So thank you again, Scott, and I'll now give control to Shri, who will talk to us about bolt and disk decompositions with SAMI.